Good morning, this is our team and welcome to our presentation. First of all, we're going to introduce the table of contents of this template.
We are going to start with the introduction. Mixing is one of the most widely used operations in the industry due to the high number of applications. Like many other operations, many factors can influence the efficiency of this process. One significant factor is the geometry, especially the impeller's geometry, since it can define the hydrodynamics of the fluid. The objective of this project is to determine what is the effect of implementing baffles to a stirred tank, mainly on the flow patterns, power pumping, and overall performance of an agitated system in an impeller S-FAR.
Afterwards, we have our materials and methods. First, the geometry and the assembly was made at Autodesk Inventor on the CAD side. On the CFD side, we have to define the faces and the interfaces between our bodies, and we're going to establish and generate our mesh. Then we are going to determine the physical conditions of the system, and we're going to run our simulation and contrast the results with those in literature. As it can be seen, table number 1 shows the main measurements used for our design of S4 impeller and both of our tanks. It is important to mention that the measurements were based on the design of a standard steering system. Below are the measurements of the unbaffled tank. In the figure, it can be seen the two rotation zones created for the system. In the same way, in this figure, the measurements of the baffled tank are presented. In them, you can see their dimensions. Afterwards, the impeller measurements are presented. For the creation of the impeller, different bibliographic sources were taken into account, most of which suggested that the blade measure must be between 50% and 80% of the diameter. For this case, 75% was taken. Finally, the measurements of the rotation zones for both tanks are presented. During its creation, the recommendation of Lane and Koch was followed, in which it is recommended that the rotation zone of the impeller should be 2% greater than the diameter measurement.
A polyhedral measure, Prim's-Lear measure, and a surface remeasure model were taken into account for the mesh generation of the unbaffled tank. Table 2 shows the parameters used for the mesh generation, from which we highlight a value of 0.02 for the base size and 2 Prim's layers. The same models and parameters were used for generating the mesh of the baffled tank, except that the Prim's layer thickness and the relative minimum size were changed from 5 to 9%. The properties of the water to carry out the simulation are 1000 kilograms per cubic meter for the density and 0.001 pascals times second for the viscosity. Steady and unsteady states were modeled as well as transient and turbulent regimes. The summary of the physical models for both states are shown in tables 4 and 5. The only difference is that one has the steady model and one has the implicit unsteady model. The shear stress transport kappa omega model was used in this case because it combines the best of the kappa epsilon and kappa omega models. It has an excellent operation in a wide range of Reynolds values, a great application near the wall, and a lower sensitivity to the inlet free stream turbulence properties in comparison to other models.
Then, the following suppositions were made for the development of the simulations. First, fluid at 20 degrees Celsius. Second, heat transfer effects were not taken into account. And finally, a standard tank was taken. For the initial conditions, the atmospheric pressure of Bogota was taken, and for the boundary condition was taken as follows. The sleep condition at the superior face of the tank and no sleep condition in the wall interfaces. Finally, a total of 4 simulations were performed for different Reynolds number for each tank as shown on the screen. A machine dependency test was developed for the baffled tank to determine the effects of the variation of the target size parameter and the number of cells. in the computational requirement. In this way, three types of mesh were generated. For the purpose of the work, the reference mesh was selected as is allowed for a greater power number in computational time, as is shown in the comparative figure. However, the source value is very low, therefore errors were generated to describe adequately the phenomenon that governs the system.
The power number is a function of numerous variables, such as the type of impeller, the Reynolds number, and geometric parameters such as the diameter of the tank or the diameter of the impeller. In the figure, you can see the behavior of the power number as a function of the Reynolds number, in which, for example, you can see that the unbaffled tank has a constant behavior on turbulent regime. On the other hand, we can see that the presence of baffles has a significant effect of the number of the power number in turbulent regime, where its value increases significantly. Figure number 7 represents the pumping number as a function of the Reynolds number, and as it can be seen in the graph, the results are not in agreement with the results present in literature. This is due to mistakes in calculation of the outgoing mass flow at the lateral interfaces. It is unknown if the error rate comes from the method used to calculate the flow of mass going out the surface or from the inefficient meshing which we worked.
Reynolds versus the brake power curve for the flat-bladed turbine is shown in the figure 8. In the transient regime, a higher number of pumping is obtained for the tank with baffles, while in the turbulent regime, the number of pumping is higher for the tank without baffles. The Reynolds versus the power index curve for the flat-bladed turbine is shown in the figure 9.
The figures 10 to 13 show the vector velocity profiles for the different Reynolds number for baffled and unbaffled steering tanks on steady state. As is shown, the liquid flow has a radial component. The agitator blades create a radial flow outward from the agitator, so there are zones of recirculation toward the top and bottom of the tank. The increasing Reynolds number indicates increasing fluid velocity. The figure shows the formation of vortices and eddies at higher. As can be seen, by implementing baffles, the fluid movement is controlled. The baffles prevent the entire fluid mass from rotating around the shaft. They also prevent the formation of a vortex in the center that can damage the agitator and introduce air into the product. As can be seen, the higher velocity is observed at the tips of the impeller. The same way, figures 14 to 17 shows the same behavior in the velocity profiles that shown previously. As it can be seen for turbulent regime, velocity is higher in the tips of the impeller.
Figures 18 through 21 show the Y plus value from the impeller when working with different Reynolds values. Figures 18 and 19 show the scenes when working with Reynolds of 100 and 1000. As it can be observed, there's practically no difference between the Y plus scenes. On the other hand, figures 20 and 21 work with Reynolds of 10,000 and 100,000. As it can be seen, where the Reynolds increases, the Y plus value increases as well. This is because the Y plus depends directly on the kinematic viscosity. Figures 22 through 25 presents the pressure profiles for different Reynolds numbers, as it can be seen on figures 22 and 23, which presents the results when working with values of 100 and 1000 for Reynolds. Regarding all the pressure scenes, the values are greater on the blades than in any other part. Also, as the distance from the disc increases, the pressure decreases, as it can be seen by the color of the impeller's axis. Moreover, figures 24 and 25 show the pressure profile for Reynolds of 10,000 and 100,000. Concerning all the pressure scenes, it can be concluded that because water vapor pressure is of 2,333 pascals, there is no cavitation present in any of the simulations.
Then this animation presents the streamlines for an unbaffled steady state and a Reynolds of 1000. Can you see how the fluid moves gradually with a low velocity? Then this animation presents the streamlines for an unbaffled steady state with a Reynolds of 100,000. In comparison with the previous one, it can be seen how the fluid moves with a higher velocity and presents more eddies.
This animation shows the streamlines for a baffled steady state for a Reynolds of 1000. It can be seen that the mixing is improved when the baffles are placed. It also observed that the flow is radial when leaving the impeller, and when hitting the baffles change its behavior. The same can be said in this animation for a baffle steady state with a Reynolds of 100,000, with the difference that having a higher Reynolds has a higher velocity, so it is so much more chaotic.
This animation shows the vector velocity of the fluid when agitated in an unbaffled tank. It represents the flow accordingly to theory. It can be perfectly observed the radial flow that corresponds to this impeller. As time passes by, the magnitude of the fluid near the impeller increases. This animation is for the non-steady state flow in the baffled tank when the Reynolds number is 100,000. Similar to the previous animation, it can be observed the radial flow of the fluid when agitated by the impeller. Moreover, the velocity increases where the agitation takes place as time passes. Regarding the difference between the two tanks, the baffles decreases the number and sizes of dead zones, fulfilling its purpose.
Lastly, we got our conclusions. First of all, on the geometry side, we consider important to analyze the influence of the blade length on the response variables for future simulations. On the other hand, for CFD simulations, we believe that it is important for in the future to guarantee better mesh that have a lower percentage of error. We also propose to follow cost methodology for the calculation of the flow volume, and thus to be able to correct the numbers of the pumping number. Finally, for future work, we intend to analyze the S4 stirrer focused on its main function that is, with simulations for the preparation of emulsions in which new variables are evaluated.